Swayam Prabha. Digital India. Educated India.
Hello, welcome back. This is lecture number 5. In the last lecture, we discussed about the induced drag, the vertices which was created at the tip of the wing, and because of the vertices at the tip of the wing, the angle of attack experienced by the wing is actually reduced by how much? By induced angle of attack alpha I. Alright, and we were in a process of finding the exact variation of this induced angle of attack, and in fact we can actually calculate what is the variation in this drag. Alright, now let us quickly go back to the figure that we were referring to. So we have drawn this figure in the previous lecture. Here we have the lift vector is now inclined towards the local relative flow. Alright, the lift vector is now inclined towards the local relative flow, but not to the free stream velocity. Alright, and here alpha g is geometric angle of attack, alpha I was induced angle of attack, the angle has reduced by alpha I, and finally the angle of attack seen by the wing is the effective angle of attack, which we are denoting it as alpha effective. So alpha g was alpha I plus alpha effective, and alpha effective equals to alpha g minus alpha I. Now if you notice this lift vector carefully, and we can actually resolve this lift vector again into two components, one parallel and perpendicular to V infinity. Remember, we always define or resolve the component with respect to V infinity. Alright, so now there is one component of lift which is actually contributing towards the induced drag. Okay, and of course the one component which is at perpendicular to the V infinity, which is this one. But there is a one component of lift which is actually contributing towards the induced drag. Okay, so that we can mention here as, that can be mentioned here as di equals to, or let me write here, di equals to L into sine alpha I. Alright, so since alpha I is small, so we know that for small angle of attack, sine theta is approximately equal to theta, cos theta is approximately equal to 1. So in this case, induced drag can be written as di equals to L into alpha I. Okay. Now this alpha I we can consider from elliptical lift distribution. We'll come to this term, elliptical lift distribution. What exactly is that? But let me write from elliptical lift distribution. Okay, that is lift per unit span that varies elliptically along span. Okay, and from the elliptical lift distribution and incompressible flow, theory, alpha I can actually be derived as CL by pi AR. I am not going into the derivation of this. This you can view it from any aerodynamics book, even from the J.D. Anderson book, even from the aerodynamics book, you can find this relation as alpha I equals to CL by pi AR. Alright. Now what is elliptical lift distribution? If you have a wing in this way, okay, so this is the front view of wing. So what happens is the lift is actually distributed in this way. So it is an elliptical lift distribution. So this is elliptical lift distribution. And in the bottom we have the downwash component W. Downwash component W. Alright. So now di is written as L into alpha I. Alpha I is L into CL by pi AR. Now again we divide by Q S, that is Q infinity S on both sides, dus b dot s both sides. So we write here as di by Qs. Again, if I'm not writing infinity, assume this is infinity over here. So di by Qs equals to L by Qs, CL by pi ER. And this we know from our previous classes, and that we have been repeating again and again. So this is CDI equals to CL into CL by pi AR. And finally we get CDI equals to CL square by pi AR. Okay, induced drag is given by this expression CL square by pi AR. Now here, for this elliptical lift distribution, this is assumed to be having exactly an elliptical way. Alright, but actually because of the losses due to the interference effects or structural constraint, due to interference effects or structural constraints, alright, or due to losses, we never obtain exact elliptical lift distribution. Okay, so we do not get elliptical pattern. We do not get an elliptical pattern. So for example, if this is the front view, so we will be obtaining something like this, the lift distribution. Okay, so this is non-elliptical. So that means what? The further CDI will increase, CDI increases further. So we can include this factor of non-elliptical lift distribution by a term known as span efficiency factor. Alright, span efficiency factor, or it's also known as Oswald efficiency factor, denoted by C. Okay, so for subsonic aircraft, its E value is approximately 0.85 to 0.95. Okay, so this is always less than 1. So we write here as CDI equals to CL square by pi E AR. So that means if this number is less than 1, then CDI will obviously be increased. Alright, CL square by pi E AR. Okay, and this 1 by pi E AR is generally written in terms of K. So finally we get K into CL square, where K is nothing but induced drag correction factor. Okay, K is the induced drag correction factor. So here induced drag, you can note here that induced drag is actually varying as a square of lift coefficient. Okay, but what happens At high angles of attack, we know at CL versus alpha curve, as the angle of attack is increasing, at high angles of attack, CL also will be very high. Okay, so CL will be maximum. Then induced drag will also be substantial portion of the total drag. Alright, so let me write down here. Induced drag varies as square of lift coefficient. So at high angle of attack, PDI can be substantial portion of total drag. Alright, and one more thing, we can actually reduce this induced drag by increasing the aspect ratio. We increase the aspect ratio and CDI actually reduce it. Alright, now finally we can write here as CD equals to CD plus KCL square. Alright, now this is because drag due to lift. This is the drag due to lift or induced drag. Okay, if there is a lift, there will be induced drag as I mentioned before. So whatever other types of drag are existing, that is because of the empennage, because of the engine, because of the fuselage, that we call it as zero lift drag. Okay, so let me write here GCD naught plus KCL square. So this is zero lift drag and this is induced drag. So finally we obtain CD equals to CD naught plus KCL square. This is very famous equation. So this equation is known as drag polar equation. Okay. Remember I have drawn a curve plot between CD versus CL in one of the earlier lectures. Alright. So this was something like this parabolic curve. So plot of CD versus CL is known as drag polar. Alright, the plot of CD versus CL is known as drag polar. So complete aerodynamics of an airplane is reflected in it. Complete aerodynamic of the aircraft. So whenever any company, for example, aircraft companies, airline companies, they procure or lease aircraft from the aircraft manufacturers. So in the technical details, this will always be mentioned about drag polar. What is CD naught? What is K? Okay, so this is the basic equation, that is drag polar equation. Okay. Now for this, now that we have considered for 3D wing, that is for the finite wing where we have the finite, where we have tips of the wings are existing. So what happened to the lift curve flow? Alright, that is the question that we need to ask. What happened to the lift curve flow? We have addressed the question that CL will actually be reducing when compared with C small l, and CD capital D will be increasing when compared with the small d. But we did not discuss about the lift curve slope CL alpha. So what about the 3D lift curve slope CL alpha? Will it be equals to CL alpha or not? If not, what is the expression? That is the question we need to address. Alright, so let us quickly address it. So now we have a 3D lift curve slope. Okay, that is CL alpha. Fine. So remember, the C small l alpha was like this. This is CL, this is alpha. I mean, again and again, I will be drawing this figure, this plot, so that it embeds in your mind. So this is CL alpha, that is nothing but the flow. Alright, so this is applicable for infinite gain. Okay, or a 2D flow. Okay. So let me also write the induced angle of attack expression that we can write maybe pi AR or pi E AR as well. Okay. So now for infinite wing, how much is your aspect ratio? Aspect ratio was what? Aspect ratio was d square by s. Now span is infinite, so your aspect ratio will become infinite. Okay. So for infinite wing, aspect ratio is infinite. Alright. Then if this is infinite, then alpha I will be what? Then alpha I obviously will be 0. Okay. Then remember alpha G expression was alpha effective plus alpha I. Then we found alpha effective to be alpha G minus alpha I. So when aspect ratio is infinity, okay, alpha I equals to 0. So that means the effective angle of attack will be exactly equal to the metric angle of attack. Okay, is that clear? Now let me draw a plot for this. So let me consider symmetric airfoil, not the cambered airfoil. Let us keep the things simpler. Alright, so let me write here CL, and this is alpha, and assume this is the CL versus alpha curve. Okay, so this is for aspect ratio equal to infinite. That means our infinite ring. Alright, and consider one point, that is CL star. Consider this point as CL star. Okay. Now, obviously, the aspect ratio will be finite for the real aircraft. So, when the aspect ratio is finite, so then your alpha effective will be what? Or your geometric angle of attack is alpha effective plus alpha I. Okay. So now alpha I will not be equals to 0. So to produce this CL star, it required as an alpha effective. This angle of attack was required, which is alpha effective. Okay, so this for aspect ratio equals to infinite. Now for finite wing, for the same CL star, the angle of attack has to be increased by how much amount? By alpha I. Okay, so if you want to produce same CL, in this case CL star, here it has angle of attack has to be increased by alpha I. Say for example, consider this point, and this is alpha I. Okay, so now your plot will actually go like this. Okay, this is for another same CL star. This is alpha effective and this is alpha I. Now this is aspect ratio is finite. Now can you comment about the lift curve slope? This is CL by CL, dCl by d alpha, and this is also dCl by d alpha. So this is C small l alpha and this is C capital L alpha. So now can you comment, has your slope increased or decreased? Okay, so it is clearly visible, your slope has actually reduced. So CL alpha is less than C small l alpha. Okay, and please note that 3D lift curve flow will always be less than a 2D lift curve flow. Okay, fine. Now this was applicable for symmetric. We'll come towards cambered as well, but as of now, first of all, let us find the relation between the Cl alpha and small Cl alpha. Okay. So now when aspect ratio was infinity, the Cl alpha, Cl star can be written as, remember the equation? Cl equals to Cl naught plus Cl alpha into alpha. So here it is Cl curve is starting from 0 at alpha equals to 0. So there is no intercept. So Cl naught is 0. So Cl equals to Cl alpha into alpha. Okay. So if I have considered Cl star over here, so Cl star will be Cl alpha into alpha. Now what is alpha here? Alpha effective. Okay, this is alpha effective. This is for Cl star. For this Cl star, this much angle of attack needs to be, we need to have this much angle of attack. Alpha effective Cl star equals to Cl alpha into alpha effective. This is equation number 1. Alright. Now for finite wing, so say this is the finite aspect ratio. To generate Cl star, again there is no intercepts. We will be having Cl alpha, and here it should be small l alpha. Okay, so this is for 2D. This is for 2D infinite. Now this is for finite. Now we will be having a capital here. Cl alpha, Cl star equals to Cl alpha into alpha. So here alpha will be is increased by induced angle of attack alpha effective plus alpha I. Okay. Right. Now what is alpha I? Alpha I we actually calculated. We know already alpha I is Cl by pi E AR, and Cl we considered here Cl star. Okay. Now what is the unit of this alpha I? So many students will say it is in degrees, but actually it is not. Cl unit, it is dimensionless. Aspect ratio is dimensionless. E is Oswald efficiency factor is dimensionless. Pi is also dimensionless. So this unit is actually in radian. Okay. And we know how to convert from radians to degree. We just multiply by 57.3 Cl star by pi E AR. Okay. So now from equation 1, you can easily write alpha I equals to 57.3. Cl star is given as C small l alpha into alpha effective divided by pi E AR. Okay. Now, what happened to Cl star? That in the previous equation that we have mentioned for a finite wing. So Cl star we can write here as Cl alpha into alpha effective. Remember this is in degree. Okay. So plus alpha A is this much 57.3 P small l alpha effective divided by pi E AR. So this is equation number 2. Now see here Cl star is actually same, whether it's for infinite or finite wing. Cl star is actually the same, it is same constant. So since Cl star is same, equating equation 1 and 2. So what do we get here? Cl alpha effective, P capital L alpha into alpha effective, I am taking common. So get 1 plus 57.3 Cl alpha upon pi E AR. Alright. And finally we can write C capital L alpha equals to C small l alpha divided by 1 plus 57.3 Cl alpha by pi E AR. So this is the relation between a 3D lift curve flow and a 2D lift curve flow. So you can verify here. So if aspect ratio goes to infinity, this term will be 0. So you will get CL alpha equal to C small l alpha. Okay. For 2D ring, for 2D airfoil, we have CL alpha equals to CL small alpha. Okay. Now after that we have now that we have derived the relation between CL alpha and small CL alpha, and we have also plotted the curve for this symmetric airfoil. Now, if in case I would have considered cambered airfoil, okay, remember the cambered airfoil, which was for cambered airfoil. Cambered airfoil, even we have CL at 0 angles of attack. Alright, so we know that the slope will actually be reduced for a 3D lift curve flow. But what about this point? This point is CL at alpha equals to 0. Alright, so will that point remain same? Will this point remain same for both the plot, that is for infinite wing, finite wing? Now my question is, for this cambered airfoil, the CL at which alpha is 0, will this point remain same for both infinite and finite wing? Now let us look what happens to the curve for cambered airfoil. Okay. So when lift is 0, this we know alpha I is equal to CL by pi ER. Okay. So now when lift is 0, for both, it can be for both, for infinite and finite wing. When lift is 0, then what happens is alpha I equals to 0. So that means there will be no induced angle of attack. Alright. So now if I quickly plot CL versus alpha curve for a cambered airfoil, alright. So this was for aspect ratio infinite, and this is for aspect ratio finite. So it should start with at the same point. Okay. So here we have alpha at which CL equals to 0. So this is for aspect ratio finite. Alright. So since at CL equals to 0, there will be no induced angle of attack. Alright. So that is why this alpha at which CL equals to 0, that point will remain same for both the curve. Hence, we can say that angle of attack for 0 lift that is alpha at which CL equals to 0 is same for finite wing is same for finite and infinite wing. Thus alpha CL equals to 0 is directly obtained from where? Is directly obtained from the wind tunnel result. Wind tunnel test. Okay. So now finite wing has two major changes. Finite wing has basically two major changes. Your induced drag must be added, that is as discussed earlier, CD equals to CD naught plus CL square. Okay, so this is CD0 is nothing but again profile drag. Please do not forget these names, profile drag or zero lift drag. Okay, and this is KCL square, and this is the induced drag or lift drag due to lift. As I explained previously as well, nothing is free in this life. You get lift, there will definitely be drag. Alright, CD equal to CD0 plus KCL square. Please remember this drag polar equation. And second observation was that lift curve slope of finite wind is less than lift curve slope of infinite wind. Alright, please do not forget this fact. PL alpha will be less than PL small alpha. Alright, now can we in this plot, so in this plot you must have observed that this is CL max, so this is CL max. Alright, now are there any ways of increasing the CL max? That is the next discussion. Methods of increasing CL max. Okay. Now let us put here again the figure. So this is CL max. This is CL and this is alpha. Okay. And this is the angle at which there is a flow separation happening, and that phenomenon is known as stalling, as we discussed in the previous lecture. So this angle is alpha stall. Okay. Fine. Now, are there any methods of increasing this CL max? Okay, that we are interested in knowing today. This, if you see this expression, CL equals to 2W by rho s V square. Alright, so I can write here V equals to 2W by rho s CL. So this was for steady level flight, lift was equal to weight. Okay, so V equals to square root of 2W by rho s CL. When the aircraft is flying at this angle of attack, that is alpha stall, where we have CL max, so then we can write velocity as V stall velocity 2W by rho s CL max. Okay, so this is the stalling velocity. Now, when I ask this students about what is stalling velocity, by giving an example, that for example, if one aircraft has a stalling velocity of 100 meters per second, and another aircraft 2, has a stalling velocity of 80 meters per second. Alright, one aircraft is having stall velocity of 100 meters per second, and another aircraft is having stall velocity of 80 meters per second. So generally, my question to the students would be, as an aircraft designer, which one will you prefer? The one with the lowest stall velocity or the one with the highest stall velocity? Okay. Now, first of all, we need to understand what is stall velocity. You know? Stall velocity is nothing but the minimum velocity with which aircraft can fly. It is the minimum velocity with which the aircraft can fly. Okay, this is also known as stalling speed. stalling speed. Okay. So for level and straight and level flight, this is given by this expression. So the Vstall definition is the minimum velocity with which the aircraft can fly. Now, which is most preferable, the stall velocity of 80 meters per second or 100 meters per second? Alright. Now, the answer is obviously 80 meters per second. Why? Okay. Now, during takeoff, as I said, aircraft needs to have a certain velocity so that there is a certain amount of pressure difference created between the lower and the upper surface of the airfoil. So, if Vstall is or if the minimum speed is 80 meters per second, so as soon as the aircraft achieves 80 meters per second, technically speaking, then aircraft can take off. But of course, there is a factor of safety. That is another point. The point here is, so aircraft only needs to go to 80 meters per second and then it can actually take off safely. Alright. But if the Vstall is 100 meters per second, then the thrust has to be increased in such a way that the aircraft is traveling at 100 meters per second. Alright. Okay. So obviously we would not like to strain our aircraft engine. Okay. So we can, instead of these numbers, let me write in kilometers per hour. So that will make more sense. So 100 kilometers per hour, for example, and another one is 80 kilometers per hour. Okay. So with the one with the lower velocity, that stall velocity is actually preferred. Okay. So at low velocity, aircraft is actually flying at CL max. Similarly, during landing, we would like to touch the ground at the lowest speed, not at the high speed. Okay, that is also one of the reasons that minimum velocity we would like to have during takeoff and landing so that it takes off safely as well as lands safely. Okay. So by the definition, you can understand where the Vstall is the minimum velocity with which the aircraft can fly and the lower velocity is preferred. Okay, I hope I have spent much time, at least this is clear by now. Now, higher the CL max, the lower the stall velocity. So this is inverse relationship as we know. Higher the CL max, then lower the Vstall velocity. So again, aircraft designers try to increase CL max and thereby reducing stall velocity. But for a given airfoil, CL max is fixed. So for example, 2412 airfoil, your CL max will be actually fixed depending upon the speed. Alright. So then what we do is we employ artificial high lift devices. Artificial high lift devices that will increase the CL max. Okay. The most common one is flap at the trailing edge of the wing. Flap at the trailing edge of the wing. Okay. So let me draw a figure for flap. This is nothing but a flap. Now we plot with a in flap deflected one. Let us suppose this flap is deflected by an angle, say delta. Okay. Now let's plot it again. Now let us assume this is as point A and this as point B. Alright, and let us point directly with the trailing edge. So this is nothing but delta alpha over CL. So now let us see what is actually happening over here. So flap is deflected by an angle delta. Okay. So CL is, so then what happens? As soon as this flap is deflected, then CL is actually increased. Why? The CL is increased due to the following reasons. Okay, the first reason is as the flap is deflected, now you can see the camber of the airfoil has actually increased. Okay, the camber of the airfoil is increased. So higher the camber, the more the CL. Alright. So camber of airfoil is section is increased. The more the camber, higher the CL. Okay. And second point is, see, note here that there is a virtual increase in angle of attack. If you draw a chord line directly between this point and this B point, there is a virtual increase in angle of attack. Okay. Then this also ensures CL is increased. So there is a virtual increase in angle of attack by virtual chord line okay, and CL is increased and CL is increased. See here, note that the lift curve slope, if you notice here, the lift curve slope is shifting towards the left hand side. 1 second. The lift curve slope, let me draw the plots for the lift curve slope. What exactly is happening to the lift curve slope? So this is with delta equals to 0. Okay, so there is no flap. There is no flap. Similarly, if there is a deflection in flap, then delta equals to, say, for example, 15 degrees and delta equals to, say, for example, 50 degrees. Alright, so this is CL. So there can be increase in CL by 2.0 as well. Okay, so this is the alpha at which CL is 0. This is the alpha at which CL is 0. Alright. Now here, if you notice these figures carefully, this is CL versus alpha curve for again cambered airfoil. Please note that the lift curve slope is actually shifting towards left and CL is actually increasing. Alright. Note that lift curve slope shift towards the left. However, alpha stall is decreased. See here, alpha stall is actually decreasing. However, alpha stall is decreased. That's okay. Even if alpha stall is decreased, we have successfully increased the CL max to certain value, which is more than sufficient during takeoff and landing. Alright. Also, alpha at which lift equals to 0 shift towards more negative value. Alright. But one thing to note here is, what about the CL alpha curve? Is there any change in CL alpha curve? No, there will not be any change in the CL alpha curve while deflecting the flap. Alright, so CL alpha curve remains unchanged. Alright, now this, instead of flaps rotating downward, it can also translate rearward. Alright, instead of let me write down, instead of rotating downwards or flap rotating downward, it can also translate rearward. It can also translate rearward. So that means these surfaces can actually go inside the wing. Alright, that is translate rearwards, which is actually quite common in passenger aircraft. So if you notice carefully, if you get chance to sit over the wing, then please note that these small surfaces, flaps, can actually translate rearward. Alright, which is quite common in the passenger aircraft. So which will increase again CL max, okay, by a factor of 2. Now we have talked about the flaps. There are certain surfaces also is kept in the leading edge of the surface. Alright, so if we keep one more surface over here at the leading edge, and then further this camber is actually increased. Alright, so these are generally called as slats. So these are also can be easily observable from in the common passengers aircraft. Alright, so if we use slats at the leading edge, or slots in the surface, then CL max can be increased by a factor of even 3. Yes, by a factor of even 3.0. Alright, so now actually you are encouraged to look for more high lift devices. Okay, you are encouraged to look for more high lift devices with which CL max can be increased. Alright, fine. Now let us consider the previous example of the Cessna 172 aircraft. Remember, we have considered Cessna 172 aircraft. Let me show you the image again. Yeah, so this is the Cessna 172 aircraft. Alright, so we'll use this data of the same aircraft again and find out the lift curve slope. Alright, we'll write here example. Consider same aircraft. Cessna 172, where we are interested in finding the 3D lift curve slope that is CL alpha or DCL by PL. Alright, now given again the same parameters, that is wingspan, V equals to 11 meters, wing area, capital S equals to 16.2 meters square, Okay. Chord length is given by C equals to 1.5 meters. Okay. Now, when the span is given, when the area is given, so immediately you should actually find what is the aspect ratio. Okay, aspect ratio is given as B square upon S. Alright, so here B is 11, so 11 divided by the wing area is 16.2. Okay, now what will be the unit of this? It is 7.46. What is the unit of this? Yes, there will be no unit since it's a dimensionless number. Alright, so always check for dimensions if you ever have any question related to the units. Alright, now let us assume the Oswald efficiency factor. Oswald efficiency factor or span efficiency factor as 0.95. Okay, this is again typical for subsonic wings. This is typical for subsonic wings. Remember, I told you the efficiency factor or Oswald efficiency factor is approximately 0.85 to 0.95. Alright, Oswald depended upon the elliptical lift distribution. Okay, please do not forget the basics, elliptical lift distribution. And this will never be equals to 1. Okay, this will always be less than 1. Alright, so if you want to know more about this elliptical lift distribution, search about Spitfire aircraft. So it was a fighter aircraft used during the World War. Alright, so here what happened was the wing was designed in an elliptical shape. Okay. To encourage E equals to 1 and there is less induced drag. Okay, but the problem with this aircraft was this aircraft wing was in elliptical shape, which is difficult to manufacture. It is difficult to actually manufacture, and there are costs associated with this as well, high cost. Alright, so you can search about this Spitfire aircraft and see the elliptical platform of this Spitfire aircraft. Okay, so generally the point here is I'm trying to make here is E will always be less than or equals to 1. Okay, now the lift curve slope. Now, even if E is not given, please assume E is approximately 0.85 to 0.95. Okay. Now, the lift curve slope, 2D lift curve slope, that is 2D lift curve slope, okay, for infinite wing is equals to 2 pi. It is approximately 6.283 per radian. Okay, never forget the units. It is not unitless. CL is unitless, but not CL alpha. CL alpha is dCl by d alpha. It is divided by some angle. So it will be either per degree or per radian. Alright, most of the students will do mistakes here. So this is 6.283 per radian. Now you can convert it to per degree. Now here also students will be doing mistake. Since radians is at bottom, we need to divide this by 57.3. 3. Okay, so 1 radian is 57.3 degree. Okay, so here radian is below. So divide by 57.3, you get 1.96 per degree. Okay. Now finally, CL alpha expression we can write here. C small l alpha by 1 plus 57.3 CL alpha by pi e AR. Alright. So you can write 1.1096 divided by 1 plus 0.1096 multiplied by 57.3 divided by pi is 0.95, aspect ratio 7.546. So finally you get CL alpha equals to 0.0854 per radian or per degree? So obviously per degree, since we have already converted. Alright. So now we can finally say that finite wing produces less lift per angle of attack than an ideal (2D) airfoil due to the induced downwash. Right? I hope this topic is actually clear. Okay. So now we are ready to move to standard atmosphere, where our aircraft is actually flying. So that will be covering from the next class. All right. Thank you.